All right, good morning. Sorry I'm a little late today. Sounds like semester's in full swing with all sorts of project, homework, drama kind of stuff happening. Hopefully that's... Don't know the half of it. Well, I'll tell you what, I'm behind on these types of things too, because I realize we are now here, and I still haven't given you homework for this section. So I'm going to have to move the exam.
That's the best news I've heard in a while.
I'm so sorry, because I think partly, the membrane thing didn't go through very well, and it's just like I want to spend a little extra time on the different pieces, and so it just wasn't adding up. So.
No, we have every single week for the past 6 weeks.
Apparently, this is a good thing. I'm very glad to hear that.
We didn't get to all the notes before the test. We'll just do it after the test.
We'll give you the same test. We'll give you the same test with the notes we have at home. That's what most professors are doing. That's what our thermo professor is doing.
And then he reviews it after.
Yeah.
And he's like, so.
And then I told him that, and he told me, when I told him, he looked me dead in the face and said, "You didn't need to know those concepts. You could have solved it with math." He told me that dead to my face, and I said, "We didn't cover what we needed to know for the test."
So, take that as a vote of confidence. Just kidding. Later. It's too painful right now, right?
Yes.
No.
I solved all of his life's problems with math. That's it. Just math.
Ouch.
Yes.
I don't think it's going to be a pep talk. I think he's going to degrade us. I really think so. Honestly.
Well, that's the terrible thing is like what he said to you is both, right? It's like it's such an insult. Like I'm here to learn, and you're supposed to teach me, but at the same time, it's sort of that vote of confidence that like you could do this. Technically, you don't. I don't need to teach you any of this. You could do it all. You've learned it before, right?
That's the thing I'm trying to figure out. It's like, oh, you could have figured it out, but then he went ahead and taught us it after the fact. So like, what's the point?
Yeah.
That's thermodynamics. Should learn turbulation in high school. Sir, I did not. I really did again.
That's terrible. Okay, so yeah, so that's a bit rough. Sometimes I feel like that when I design an exam and when I've taken exams. I had one class in grad school that was like, I felt like I never learned anything in lectures. It was just, all it was slides with equations on them, and it just kind of monotonous talking about them. And like, it almost sort of made a tiny bit of sense during class, and then on the exam itself, I'd be learning, and then walking away, I'd be like, oh, okay. No idea what that was about.
That sounds painfully
in the moment.
Painfully similar. But the only thing is we'll walk away from the test and be like, y'all understand what just happened? And everybody's like, yeah.
We walked away from the test asking him if he was going to have it graded before the drop date.
Yeah, we didn't know that it's dropping live.
Ouch. Well, good luck.
He's an interesting character. He's really interesting.
Supposedly that model you're still learning something in the class. It's just that the GPA aspect kind of might suck. So hopefully the learning is what ultimately is important. Okay, so that's not my plan. I was gonna. Okay, so given that I'm gonna move the exam date, it's very likely gonna be, we need today. I'm sorry, we're not even on the 26th. Today is the 28th, right? So we're here today, and we need 2 lectures at least on the hardness, alkalinity, and softening. So I want to make sure that we're all kind of on the same page there. So that's putting us, into the second for this topic. I also need to give you at least a week for the homework. And so at earliest, we'll do the exam review would be the 4th, and then we'd have an exam on the 9th. I'm giving an exam in my other class that day, so I'm kind of hesitant to do both in the same day. But if you guys have a preference between the 9th and the 11th, let me know, and I can probably accommodate.
I'm the only one with a conflict on that.
Right. So I'll probably aim for the 11th. So
I wouldn't want to put that on.
Yeah, I'm fine with either ways.
she'll be fine if I put the same problem on both,
Yeah,
right?
I did much better on the 2000 type than I did on the 3110 fast.
Which honestly, I'm kind of down for.
She's got the whole plan.
Okay, so-
She got the planner out.
So I'm probably going to do it on the 11th. I'm going to work on this probably tonight or tomorrow. I'll get you a homework tonight or tomorrow in both classes. And so that's my plan right now. A bit of an adjustment. And I'll send out an email kind of announcing that when I update the syllabus as well. Okay, that's probably going to give us a little less time towards the end for some of the fancier things, but we'll still get to wastewater and kind of some of the essentials for wastewater design, schematic wise. So that'll get updated a little bit as well. And yeah, so there we go. So let's get to it today with hardness. Hardness is sort of the underlying reason why we want to soften water or adjust the aspects that relate to relate to the kind of mineral content. So softening is about, hard, soft water, all that. It's really about mineral content, and specifically, as we'll see in a minute, it's the content of multivalent cations. So if we're talking about calcium, Ca2+, or magnesium, Mg2+, those are the most common ones, and we can quantify that in some way. We'll talk about in more depth. And then we can say, okay, well, water with some amount of it is considered soft. If you have more than that, it's, moderately hard, up to hard, and so on. You get very hard water. You can see this map of the US with different hardness values as color gradients. Talked about this briefly before. And so this is motivating a lot of what we are going to deal with in terms of hardness and alkalinity. Alkalinity is related, but a little bit distinct. Sometimes we might just simply need to be controlling the amount of the corrosivity of the stuff. And you know what? I am tired of this. I'm just going to do it. So the corrosion control relates directly to alkalinity as well. Now, when we're dealing with both cases, hardness and alkalinity, we're really talking about it in specific terms because neither are specifically just calcium or just X or Y. So when we're considering them, we have to pay attention to how to quantify them. And we're going to do that with a couple different terms, milliequivalents per liter or equivalent weights. Before we get to all that, I want to go back over the hardness, the carbonate system. And how many of you guys have already taken EVEG 2, the chemistry course? Because it's not technically a prereq, so it's, I guess, some people might be taking it at the same time or have already taken it or not yet. So the in-depth look at the carbonate system and these types of systems, I expect to put that on that class for you to learn, to teach you, but obviously some of you haven't gotten there yet. So I want to either remind or introduce you of the carbonate system. Hopefully, or perhaps you would have seen it in EVEG 2000 a little bit, or at some other point. I don't know specifically, and I'm teaching that class for the first time myself. So, Madeline has a taste of it there, and we're kind of doing similar things right now. So anyway, carbon dioxide is going to dissolve into water. We'll get aqueous CO2. That's then going to, and that'll be driven, by the way, by Henry's law, equilibrium between atmospheric CO2 and dissolved CO2. You'll get a reaction between CO2 aqueous, dissolved gas, plus water. Of course, now that I have my mask off, I'm about to sneeze. This is going to be in equilibrium with carbonic acid, H2CO3. Because we have, essentially, we're just merging those two. So that, and then from here, we go through the equilibrium equations, We were talking about equilibrium equations last time a bit with chlorination, and we have these different reactions that are going back and forth, and you can plot them essentially as what fraction of the water is in each particular form. So HCO3 being over here, H2CO3, excuse me. So that's carbonic acid, bicarbonate, you see all these listed here as well. Bicarbonate being here, HCO3 minus, and then just carbonate, CO3 2 minus over there. And so essentially all three are going to exist in water. If there's any carbonate in the system, all three will be there, but it's what portion of it. And this is a log plot here, and technically the pH is log as well. So what we're looking at is that log fraction. So 10 to the minus fourth, there's that much bicarbonate at pH 2. There's really a very, very, very small amount, very small fraction of carbonate down, 10 to the minus 7th at pH 5, right? So there's an exceedingly small amount. Technically, I guess there's some. But you can see, you've seen these before. This is that equilibrium plot, and we have points where those two are equal. That's going to define our pKa. Going to be a little bit temperature dependent. It'll shift a little bit. We're not going to deal too much with that. Leave that to the chemistry course. So the equilibrium with the atmosphere is what adds it in there in the first place, and then it equilibrates depending on what the pH is, and that could also potentially influence the pH a little bit, because this H2CO3 is going to be in equilibrium with HCO3 minus plus H plus. So if our pH was near neutral to begin with, then you have CO2 added. We're going to first have this carbonic acid, then that's going to dissociate into bicarbonate and H plus. So that's adding some acidity to it. That means if we have pure water forming in the atmosphere and then it equilibrates with the atmosphere that has CO2 in it, we get acidic water, slightly. It's going to add just a bit of acid. So we're going to solve a problem on the pH of natural rainwater and work through an example of that here in a moment. So the governing reactions, I sort of just demonstrated them a moment ago, but we have that just to recap from our book, that CO2 dissolved in water, and then that's in equilibrium. We could even say, well, that's also in equilibrium. This guy here is in equilibrium with CO3 2 minus and H plus. So with all of that, okay, so that's just, yeah. So then reiterates it right there. If we take just the carbonate system, just CO2, that's what we get. Those are the reactions that are important. If we add some other source of carbonate, in the form, let's say, of calcium carbonate, CaCO3, that changes things a little bit, because the carbonate technically can escape back into the atmosphere if we were to drive it off somehow. So if we add CaCO3 as a solid and it dissolves, we get calcium and the carbonate. That's going to be in equilibrium. But if we decide, maybe we acidify this, so this converts into H2CO3, and then we degas it and drive off a lot of gas, we're going to be left with Ca2 plus, and then a situation where something else has to balance the charge. So by removing CO2, then we have a change in the pH, because that's the only thing left that can balance the charge, is the ratio of H plus and OH minus. So we have a situation with the carbonate system where if we add a solid form, calcium carbonate or some other carbonate mineral, it really starts to matter whether we have an open system that can equilibrate with the atmosphere. If we're removing the carbonate in some way, there's some extra considerations there. Or simply we can just say that's another form or source of adding carbonate to a system. So when we're considering our equilibrium systems, anything dealing with carbonate, we do have to consider whether or not there's an impact of that equilibration with the atmosphere. So when we get into softening and things, a lot of times what we'll assume is we have a closed system, or our parameters kind of set us up. We have the system in place. We know what's going on, and that's kind of how we're dealing with it is in place already. So we'll do the rainwater problem. We'll walk through the book solution to that together. That's going to be an open system because it's equilibrating with the atmosphere. And by the way, the Henry's law is really just another equilibrium reaction. Gases will partition into or out of solution based on an equilibrium constant. So it looks a little bit different, but it works effectively the same. Okay, so if we give it time to equilibrate, then essentially our equation becomes, or we could describe it here, this is the equilibrium reaction, that first one where CO2 is dissolving. And what we have here, it says CO2 aqueous. This is the same thing essentially as saying H2CO3, right? And that's in equilibrium with bicarbonate. So that's just our equation that's right here. So if we give these two time to equilibrate, then that's all it's saying, is we can write it that way, or we could have written it this way. And we have some equilibrium constant for that. We can then convert that, or not convert that. We can take the next step and compare the bicarbonate with the carbonate. We have a second pKa for that, or in this case, K2. And we could also look at the solubility constant for this other reaction, the CaCO3. So if we had all of these things happening in one system, then we need to have all three equations at play to understand and really characterize our system. So this would be that solubility product as the third component there. Okay, so there's quite a few factors that might take effect in our carbonate system. We're not necessarily always going to have calcium carbonate. Okay, so just sort of continuing on from there, we can essentially graph that plot that we made based on those equations if we put them in together. And this is kind of summarizing one way to look at it is to take the ratio of, let's say, the carbonic acid to bicarbonate, HCO3 minus. If we wanted a ratio between those two, we could draw it up like this. And that would be related just in kind of in the same way. I guess they were taking the other ones, but you see that's exactly what they did for the other ratio here. So we can take a look at that ratio. You can do it as a ratio of the total, which would give you like the bicarbonate per total, which is the y-axis here, or you could simply take a one versus the other, which is going to almost give you the total. It's almost going to be the same thing because in most pHs there's almost none of one of them, and then it's just competing between the other two. At any rate, there's just a few ways you can manipulate it, look at it, and so if you know the pH and we have the equilibrium constants, we can very easily sort through, okay, how much of each one do we have there? All right, so it's just a little bit of an elaboration there. So regarding open versus closed systems, again, the soda bottle is a great example of a highly carbonated system. You shake it and open it, suddenly it's trying to equilibrate with the atmosphere, and now you have lots of carbonic acid that was in there that is in equilibrium with the dissolved CO2, now coming out of solution and trying to escape into the atmosphere, taking a fair amount of liquid with it. So that's kind of what happens, and I think perhaps in this case, a Mentos candy was added to assist in the reaction. I believe that's kind of what's happening, by the way, is you're giving extra surface area for that process to go more quickly, to go from dissolved H2CO3 into CO2 gas. Now, I mentioned a minute ago Henry's law. If we can get that concentration, the brackets here of CO2 aqueous is kind of what we're talking about. That's going to be equal to some equilibrium constant, K, times the pressure of the gas. So if we had 400 ppm CO2, that's, remember ppm, let's say 400 ppm, and we'll assume that's by volume. That's approximately what we have in our atmosphere. If that's our value, well, parts per million is just like percent, except instead of using 100, we use 1 million, right? So this is, if we were to say, like, what percentage is that? 100 is 10 to the 2, 1 million is 10 to the 4. So if we move that 4 decimal places over, that would be 0.04%. If I did that right, so 1, 2, 3, 4. Yeah. So 0.04% CO2. It's the same way to describe it. And using this partial pressure as an atmosphere, if we're doing this at 1 atmosphere, so about sea level, so let's say if 1 atmosphere, that means that 400 ppm is then 0.04. Since that's percent, we need to do 2 more zeros here, because that's a ratio. 0.0004 atmospheres of CO2. I think that's correct. So that's all kind of baked into the units here. Just wanted to point that out. So then we could say, the concentration of CO2 aqueous is simply that 0.0004 atmospheres times that constant for CO2, the Henry's law constant for CO2. Okay, so that's the simple way to take a look at it. There are probably other ways to manipulate it, or other units you could have used, given maybe a K with a different units. I don't remember if I put the constant here. I don't think I have it here. There's a spot in the book that gives us the common constants for several gases. The problem here, we're going to step through the system, but I want to give you a moment to think about how you would approach solving the problem before we step through the example. So it's a relatively simple example that is a very characteristic one of our environmental engineering, right? It's what is the pH of natural rainwater. So that in this example it says estimate the pH of natural rainwater, assuming that the only substance affecting it is the absorption of CO2 from the atmosphere. Assume that the concentration of CO2 is 390 parts per million by volume, and the temperature and pressure are 25 degrees C and 1 atmosphere. So that puts us nearly at standard temperature and pressure, which is something we might need to consider if we're doing the gas stuff. So obviously we would need the Henry's law constant, but let's assume you had a K. Just think for a moment about how you would approach finding the pH. So let's say you know the CO2 already, because we just talked about how you'd find the CO2 concentration. So take a minute, maybe sketch a line or two out about how you're going to find pH. And essentially what that means is you're going to find the H plus concentration. So thank you for taking a moment to consider this. One thing that we'll notice the solution is going to introduce that we hadn't talked about yet is one concept that technically you probably knew, but would not necessarily have thought to apply here, is that the solution is going to have to be at a net charge neutrality. So one principle of solution chemistry is that we're pretty much always going to have charge neutrality. Something will balance any positive ion. So for every positive ion, we have to have a negative ion. This is one reason why ionic species don't really volatilize or escape into the atmosphere directly, is because you can't have charge neutrality in the atmosphere like you can in water. And so there's a fundamental issue there. If you do have a charged species in the gas phase, that's typically a plasma that has been created, which is a kind of a different subject. So that means that if we were to take a look at all the different species, we have potentially CO3 2 minus, we have HCO3 minus, we have OH minus, which was not in any of the equations here, but we know that's in water, right? We have water and we have the carbonate system here, and we have H plus. So in some sense, we could say, and I think this is what the book is going to provide us, is that the H plus is our only cation here, only positively charged species. So we could say that the concentration of H plus is going to be equal to the sum of all the negatives. But that's the sum of the negatives on a charge basis. So HCO3 minus has one negative charge. OH minus has one negative charge. But CO3 2 minus has two charges. So for every one molecule, you need two H pluses. So we're going to say it's equivalent there to twice that concentration. It's having twice the effect, essentially. So we're going to say 2 CO3 2 minus. This is actually, it feels weird to introduce this during an example problem, but I think it's it helps to see that this is another equation we can use, kind of a governing equation that builds in there, and we're going to use this in our alkalinity and hardness topics as well. Okay, so with all of that, and with an actual value here for the constant, then we should be able to establish a system of equations that's reasonable in order to solve for H plus. So let's take a look at what the book is doing. I apologize, I'm going to have to erase all that. Instead, pardon me just one moment, I'm going to duplicate that slide. So we can have one without and one with writing. Okay, so the solution here says, so we have a number of equations to work with based on the equilibrium constants, and it's introducing this charge neutrality concept that I just talked about. So it's basically explaining that we need that net neutral charge. Yeah, so that's basically what I have just said. Okay. So that's kind of that first explanation there, that charge neutrality. And it talks about that CO3 2 minus counting twice, essentially. Okay, one thing it does next is simplify. So we had those three different equations here that we were talking about with the essentially equation 1, K1, this first equilibrium constant, H2CO3, H plus, HCO3 minus, and we had the second one, plus the Henry's Law one, which we're going to just do that, and then we have a set amount. So given that we have two equations here in equilibrium, it's going to be nice if we can make an assumption, and that's what the book is going to say. I already mentioned it earlier that we're going to have slightly acidic, because if we started at pH 7 and then we have this reaction happening, that's adding some acidity, right? There's nothing else that's adding or subtracting H plus or OH minus. So we know it has to be, if we started at neutral, we have to go slightly acidic. So it's going to make an assumption saying rainfall is slightly acidic. That's going to let us simplify just to use that bicarbonate to carbonic acid one. And so essentially what they do then is say, well, we have almost none of this. That's about 0. Okay, so they just get rid of that altogether and say, okay, then our governing equation then is this guy. And so if we think about that, if we know how much, if we know our carbonic acid that was added to the system, then we should be able to find the bicarbonate. And then we also know that OH minus is related to pH, so we should be able to simplify that and solve and end up just having a solution where we have H plus equals the result of our individual reaction there. Okay, so let me take this further. Okay, so then we know we have for pH of water, the K for water, the equilibrium constant for water is 10 to the minus 14th. So that's equal to H plus times OH minus. So we can then substitute and solve for OH in terms of pH. So we'll get, we'll say OH minus is going to be equal to 10 to the minus 14 divided by H plus. Then we can substitute that into the equation we had, which was H plus is equal to HCO3 minus plus, and we'll just put this in here because it was plus OH from a moment ago. So I'm essentially inserting it here. So we have 10 to the minus 14 divided by that H plus. That means we have an H plus on each side, so we have to get rid of that. Do a little bit of algebra, and we can also insert here, we should have our other equation. So let's just track with what the book is doing here. Yeah, so that's the substitution they made, and then they simplified. Okay, so they also substituted here rather than simplifying. So instead of simplifying, they put in for bicarbonate, they went ahead and said, okay, well, let's put in the approach for that. So let me elaborate on that for a moment. So this step, what they did was they said H2CO3, actually, I'll say this. We'll say K1 is defined as HCO3 minus times H plus times that H2CO3. That's what essentially we dissolved into the system. Okay, so that gives us, since we knew how much CO2 is dissolving in based on Henry's law, we didn't bother doing that solution yet, but we will know it is a known. And we know K1, and right now they didn't even bother writing that out yet either. We can solve for HCO3 minus in terms of H plus as well here. So essentially we're just solving everything in terms of H plus, and then it will, we can simplify. So from there, we put that, we rearrange that so that we say HCO3 minus is equal to K1 times H2CO3, sorry about that, divided by H plus. That means when we write this equation again, we can say H plus is equal to, we have an H plus on the denominator for both of these. So we can just simply say that's K1 times H2CO3 plus 10 to the minus 14, all that divided by H plus. So that becomes a bit simpler, and we could then say H plus squared equals K1 times all that stuff. And I'll just rewrite it a little more carefully. So H plus squared, because we multiply both sides by that H plus, equals K1 times H2CO3 plus 10 to the minus 14. Okay, so then we solve for H plus in that manner, and it becomes fairly simple. That's related to the Kw, the 10 to the minus 14. That's related to the K1 and the amount of gas that we dissolved. So they go through and they say, okay, for the gas here, they did those conversions, found that that's going to be 1.3 times 10 to the minus fifth moles per liter of the CO2 in terms of H2CO3. They took that from a table and described, yeah, this is 390 times 10 to the minus 6 atmospheres. It's another way to do it, by the way, just it's a ratio, right? And it's a ratio of 10 to the minus 6 proportion. Then they solved that H plus squared, and it turns out once you do that, then the pH of natural water, natural rainwater, is found there to be 5.62 as our answer. So that's 2.42 times 10 to the minus 6 moles per liter of protons. Okay, that's a pretty substantial problem. Does that make sense? Kind of the process? You think you could do it if I added some sort of mineral to it, changing it just a little bit on a homework, perhaps? Might be something like that. Might be good for a homework where you have a bit of a template but a little bit more complexity. Okay, so this is like most of our equilibrium reactions and problems. It's actually mostly algebra, but knowing the thing is to know how to formulate the problem and where to, what principles to apply. Okay, so I'll make sure to give you some sort of practice on that. This is also fairly well related to the chlorine system, just in terms of equilibrium equations. So mastering one will certainly help with the other. Of course, this is an open system where we have gas exchange at play. Okay, so with that, I wanted to talk about alkalinity as our next portion of the topics. And alkalinity really is, well, hardness and alkalinity. I guess I'll start with hardness. So we talked about hardness as in terms of the mineral content. Specifically, it does include any multivalent cation, but in particular, we are talking about calcium and magnesium being the most important ones. We technically will have iron, the book even mentions strontium, Sr2+, all sorts of things would contribute to the hardness technically. But really what's important is the stuff that's going to precipitate, the stuff that's going to be at high concentrations, and those are going to be high concentrations in water that we would consider drinking, right? That's going to be calcium and magnesium. And I have a little picture over here on the side of a pipe that you can see its diameter, its original diameter, has shrunk quite a bit due to the accumulation of mineral deposits inside the pipe. That's actually what we want to happen. We just want to have it happen slowly. If you imagine if that pipe was a lead pipe or made with lead solder, but you had this mineral accumulation over time, you're never going to have a problem with the lead there, right? It's never going to be able to come out into solution. So if you operate your corrosion control correctly, then you'll have a slightly, what's the right word? A slightly precipitatory, you'll have your water effectively precipitating minerals very slightly over time. You do not want slight corrosion over time. First of all, even if you have a good pipe that's, let's say, I don't know, some cast iron or steel or copper or something, you don't want it corroding away, because eventually that's going to break and let water from the groundwater or junk, soil, bacteria, pathogens in. Of course, we're going to operate them at high pressure, so it's really just going to be water escaping. But regardless, that's bad. We don't want to do that. So we'd rather have to replace the pipes after 80 years because they've clogged up with mineral deposits than have corrosion causing other problems. So as we'll learn in when we do the Flint water crisis, the big thing was they didn't have proper corrosion control. So they were leaching lead out of the pipes that never should have happened. And if it didn't happen, if they had proper corrosion control, probably 90%, if not more, of their problems, and very likely 100% of the lead problems, would not have existed. So that really was not, it was not the fault of the lead itself necessarily. Obviously, it shouldn't have been there, but we didn't know it when we put them in. But that doesn't mean we have to replace all lead pipes. What it means is we have to have proper corrosion control. So we'll learn about that. But practically speaking, if you've ever lived in an area with a lot of hardness, you would have noticed scaling like that happen around your sink as water splashes and then evaporates. It's leaving a mineral residue, maybe on the shower head, kind of white flaky stuff. It should probably happen anywhere unless you're like on very, very pure RO type water. But it's not really a problem most of the time. Maybe it's annoying to scrub off. Hardness, also mentioned, has that ability to prevent soap from working as well. You need more soap to get the suds. If you have very soft water, sometimes that's also a little bit annoying because it feels like you never get the soap off. But that's the overall definition of hardness, is effectively a concentration of calcium and magnesium. However, it's not easy to express the concentration of two things like that. So we're going to need a better definition than just the concentration of those things, right? So we'll get to that. Alkalinity, on the other hand, is the measure of a sample of water's ability to take extra acid or extra protons without a significant change in pH. You might be thinking to yourself, well, how could that work? You know, if you're adding acid, then you're changing the pH, right? Well, the buffer system is what's going on. So in a buffered system, you have the ability for, let's say for the carbonate system, can act as a buffer where you may be adding protons, but it's just mostly shifting. It's essentially being accounted for by changes in the carbonate system, and you're not getting a big change in the actual concentration of protons, even though you've added some. So if you add acid, so a little bit of vinegar, to a bottle that's filled with baking soda, you might not actually see a change in pH because you're getting this reaction, and it's essentially off-gassing CO2 in that case. So there are cases where you have these buffered systems, and we'll take a look a little closer, where the addition of acid is not really going to make a big difference, and that's alkalinity. How do you measure that? Again, it's kind of tricky. It is sort of related to these cations and the carbonate system, and so we're going to actually use the same terms here, and those terms are essentially, delete the spam chat real quick. Every now and then I get a bot. Just if I can. Just block that. Okay. All right. So that's the thing, is we want to know how much acid can the water take, or will it take, to adjust the pH? Because if we're going to do the water softening, one of the important things is how much acid do we have to add to achieve the adjustments in pH that are going to be necessary to manipulate the carbonate and alkalinity system to essentially remove hardness, to cause precipitation, to do all that. Okay. So when we talk about these concentrations, a lot of times what we'll say is hardness as CaCO3, or calcium carbonate. We'll talk about alkalinity as CaCO3. So there's two different concepts here. One is equivalent weights, and that's the atomic or molecular weight divided by a number n. And this n is typically just the ionic charge. So the molecular weight divided by the charge. If you have a neutral species like CaCO3, then it's going to be the number of hydrogen atoms required to replace the cation there. So for CaCO3, in the case of CaCO3, the cation here is 2+. So that's going to be n equals 2, because Ca2+. So essentially this is just saying the ionic charge you're expecting that's attributed to the cation. So when we're talking, let's kind of watch how the book is defining this here for the equivalent weight of CaCO3. Calcium is 40. If we were to take a look at the periodic table, that's going to be its atomic weight is about 40. And then we have plus 12, that's the carbon. So this is Ca, this is the atomic weight of carbon. And then 3 times the oxygen here, because we have 3 oxygens, which is a nice round 100, which is why CaCO3 is kind of nice to work with, because 100 is a nice number to work with. Then we divide that by 2, because there's the 2+, and we get 50. So we have 50 grams per equivalent charge is essentially what this is talking about. So grams of CaCO3 per equivalent charge. So if we're quantifying hardness, we're talking about how much charge or charged, positively charged minerals are there in the water. So as an equivalent charge, that's what we're talking about. And the charge basis is handy because that's driving a lot of the system, whether we're talking about precipitation, whether we're talking about the pH balance, the charge neutrality balance, any of that. It's really coming down to that equivalent charge that thing is providing. And the grams, of course, is coming from, that grams per mole. Literally this is 100 grams per mole per 2 charge or equivalent charge per mole, right? So when we divide those, that ends up giving us our grams per equivalent charge, right? So that's how that unit is derived. So that means for CaCO3, it's 50 grams per equivalent, or what's a little bit more common is to go ahead and convert it to milligrams per milliequivalent. Okay, so milligrams of something per milliequivalent is pretty common. If we're just looking at calcium then, so Ca2+, N is still 2, so it's a charge of 2. In this case, the atomic weight is 40.1, and divide that by 2, it's basically 20, because it's not quite 0.1, it's slightly less than, and if you round, once you divide, then this will round down to 20.0 milliequivalents or milligrams per milliequivalent. Okay, so that's how our equivalent weight system is working. So if you wanted to quantify the milliequivalents per liter of some molecule X or some species X, So the milliequivalents per liter, that's going to be our concentration in milligrams per liter, and divide that by the equivalent weight. So essentially, that's just doing the molar conversion for us, right? All of this is actually about handling the molar differences while allowing us just to work with mass units. So it's handy to use mass units for a variety of reasons, in terms of how much of this stuff do you need to add. So it's a very engineering take to chemistry in a way. So if you take a chemistry course in a science department, they may well just be like, what in the world, why are you using milligrams? Can't we just use milliequivalents the whole way through, right? That's nonsensical. And there's some merit to that, but this is a system, and there's a kind of a convention here that works pretty well. So that's essentially what's going on, is this equivalent weight is doing that conversion for you, building that into the system so we can talk about it and leave it in just mass terms with accounting for the appropriate molar considerations. So a milliequivalent per liter, then, that's that concentration divided by that equivalent weight. So a few definitions there. I'll make sure to add, I'll probably add this to your equation sheet itself. Something you could probably know. And then taking that one step further, if we say milligrams per liter of something as CaCO3, so we're defining it in reference to CaCO3, so 10 milligrams per liter of magnesium, for example, as CaCO3 is not going to be 10 milligrams of magnesium, but it's going to have the same effect as 10 milligrams of CaCO3. It's going to be enough magnesium to have the same impact. The reason that's going to be convenient, again, is that 100 value. It's just kind of a handy number. 100 and 50 are both convenient to work with. So we have milligrams of X as CaCO3. That's going to be the concentration of X times that 50 divided by the equivalent weight of X. And that's literally just a conversion to put it into the units there. So be familiar with that, because, and we'll do a problem in a moment, because that's essentially the approach we'll be taking, is looking at how to express these units in either equivalent weights or as CaCO3. A lot of stuff just to say we can express it in a couple ways, right? And these are the particular ways that are common to do so. So just use this as a reference. It's not going to be too complicated, but it's just something to acclimate to in terms of how to express it. Taking a look at a table of all these equivalent weights, you can calculate these all for yourself if you wanted to, but essentially we have, you could take a look at the cations, anions, neutral species. Obviously we've got the charges, got the atomic weight, and then you can calculate that milligrams per milliequivalent, dividing this guy by this guy, right? So 27 divided by 3 is 9. 40 divided by 2, 20. So we can take a look at carbon dioxide. The atomic weight there is 44. And the N here says 2. That's because that's essentially H2CO3. And so we're going to have 2 charges there. Or maybe they're looking at it in terms of CO3 2- that can form. So that's kind of an interesting one. And so the equivalence there is 22. Magnesium hydroxide, the N is 2 because of the magnesium. And we've got 58.3 is the weight, all that. So you could go on each one of these and calculate. It's relatively straightforward there. All right, so let's take a look at example 6.4 from our book. It says a sample of groundwater has 100 milligrams per liter of calcium and 10 milligrams per liter of magnesium. Express its hardness in units of milliequivalents per liter and milligrams per liter as CaCO3. So that is your assignment here. let's see how you did. Okay, so the book says here we have this groundwater. Take a look at table 6.3, which I kind of brought a little bit of that forward for you there. Essentially, the contribution of calcium, we had 100 milligrams per liter. If we divide that by the 20 milligrams per milliequivalent for calcium Ca2+, that's going to give us 5.0 milliequivalents per liter. So that was coming from calcium having 20 as the value here, and we had so that 100 milligrams per liter of calcium divided by that, that's going to be milligrams Ca2+, just to be a little bit elaborate here, per liter, dividing by 20, this is milligrams Ca2+ per milliequivalent. So that's going to be 5, and the milliequivalents will come to the top. The per liter will stay there, and the milligrams calcium will be like that. So that's where that component comes from. We also have the magnesium there, and so that's let's see. Oh, I guess it solved them separate. Okay, I thought it was saying those two were both in solution, so it was asking for 4 answers, I suppose. So you could do the calcium just by itself that way, and then the calcium, and I apologize, I guess I misread it, or maybe it's just unclear. The calcium as CaCO3, then, if we were to express it that way, we could take that 100 milligrams per liter that we had, multiply it by 50 milligrams of CaCO3 per milliequivalent, and divide it by the 20 milligrams per milliequivalent. So that gives us 250 milligrams as CaCO3. If you were to take a look at the the ratio of CaCO3, the weight of that, and compare that to the weight of just Ca, so 40 to 100, that's 2/5, right? So 2 to 5 is the same ratio. And you take a look at 100 and its ratio with 250, that's also 2/5, right? So that's kind of the relationship here between this calcium as 100 compared to the calcium as CaCO3 as 250. Okay, so you don't have to know that part or recognize that or whatever. I'm just highlighting the fact that there is that 2 to 5 relationship here, because there's a 2 to 5 relationship between Ca and CaCO3. There's all sorts of little connections that will make sense, or you might notice during these problems, but you can also just go straight by the book, so to speak. Okay, for Mg2+, and I had thought that this was adding them together. If you did add them together in a problem, you just take this 5 plus this 5.8, right? But let's do just the magnesium here. This was 0.82 milliequivalents per liter and 41 milligrams per liter as CaCO3. Okay, so then they added them together. I'm sorry. So they solved for the magnesium 0.82 milliequivalents per liter and 41 as CaCO3. Same process, same deal, just slightly different numbers. So then they combined the two. So this was from calcium, this was from the magnesium. So they get a total of 5.8. The point here is you can add them together. You can't add 100 milligrams plus 10 milligrams here. Like, you can't add these two, so you have to convert them into a molar unit, sort of, or an equivalent, and then you can add them, right? That's essentially what we're talking about. Okay, so then that gives, you could also give that as 291 milligrams per liter as CaCO3. All right, does that make sense? It's just kind of maybe slightly annoying at worst, I think, just the units, but it's a handy way to deal with them. Okay, so then the next topic really is alkalinity. We don't have time to get into it, but essentially this is relying on that charge neutrality principle, and you can actually write out the alkalinity in terms of essentially the charge balance in a carbonate system, where alkalinity is equal to the negative components, including a 2 times the CO3 2 minus. So that's essentially the negative charges minus the sum of the negative charges minus the positive charge. So we'll elaborate more on that and solve a problem there next time, and then get into softening. And again, I'll email about the exam date, and I'll post a homework as well. Again, both of those updates will either be today or tomorrow. Okay, so have a good weekend.
So is the exam more than a week from now?
Exam is, yes, delayed. We're moving the exam backwards by a week, if not a week and a half. So I'll email tonight or tomorrow with the full details.